Okay, we're here. I apologize for my voice, which is, um, as I mentioned, I've been kind of under the weather for the past couple of days. And also before we start, remind there's no lab today, and then there's no computer assignment this week. So, um, okay. What we're doing is we're applying um, the event graph stuff that we've learned to modeling movement, and we're taking the simplest possible approach. We're doing it in 2 dimensions, and we're starting with just sort of a simple um, linear motion, which is unconstrained, meaning that we're not worried. We're not worried at this point about terrain, obstacles, um, any other kind of stuff. Just doing um, the simplest possible thing. Um, so today I'm just going to kind of review what we did in terms of that, and then uh, look at kind of the three simple rules uh, for directing a given mover to kind of move around, and then I'll finish up with the numerical example. I think okay. So see, I don't know. Okay, it's getting messages here. Um, okay, so remember the basic idea was that we had a starting place and a destination, and then so if we want to move from our starting location to our destination at a given speed, we want to turn that into a velocity, which is going to be a vector in the direction from our location to our destination, and the magnitude of that vector is going to be the speed. So um, our parameters, if you remember, were just basically the initial location and the speed. um, so the when we start, it's sort of basically time zero. Our initial location, our last stop location, which is state, is we're going to start with our initial location, have a zero velocity, and then we have this 9 point thing going on. And so in our run event, we initialize our states, and then the idea is that there's this a move to event that we're going to hear from somebody, and that's going to cause us to the state transition is we now have set our state variable destination equal to whatever that argument is, and then we schedule a start move event, which is where a lot of the the calculations go. So the velocity now is just to kind of unpack this a little bit. This is a vector from uh, the our last stop location to the destination. When we divide it by the magnitude of that, that gives us a unit vector in the right direction. And then when we multiply it by our speed, we now have a vector in the right direction and the right magnitude. Our last our start move time is our current sim time, and then the time that it's going to take us to get there is the distance divided by the speed. And so we can schedule our end move event with that delay amount. And then when we get to the end, that is when this end move occurs sometime later. We have we're now at the destination, our velocity zero, and we now don't have a real destination. This last bit is kind of, given the way this all works, is sort of optional, but you know. Okay, so now and this is a little bit of a review, is that we looked at something called a path mover manager. And the idea is that the path mover manager has a list of waypoints, and what it does is it simply sends the mover on to each of the waypoints in turn. And here this is the event graph for the simplest path mover manager. The idea is, okay, with the run, we initialize our next index, and then our destination is nothing at this point. And then there's a sort of start on run parameter, which is basically a Boolean that says, should we do this right away, like right when it starts, or not? And if that's true, then we have an event next waypoint, which is going to increment our next index, choose our destination based on what the path is, and then schedule a move to passing that destination. And then when we hear an end move, and we're going to hear this from here, it's actually easier to kind of look at it from the listener diagram. So that move to is going to get heard by the move to on a mover that it's been configured to be listening to. And since it's also listening, when the mover's end move event occurs, that will get triggered back here, and then that will in turn schedule a next waypoint, which will as long as we're not done. If we're done, meaning how do we know when we're done? When our next index is equal to the length of the path minus 1. Again, that more of the off by 1 business with the zero-based indexing. Okay, so let me okay, so here I've implemented it. I haven't had a chance to comment it yet. Obviously, that's so what I've done is here's our sort of not a point guy. Here, this is our simplest mover implementation. We're just implementing what we had there. So in Java, we can use this point2D, which is part of the standard Java classes. It has pretty much everything that we do need. And so we have what I call a max speed, and then initial location as parameters. Our states are the last stop location, velocity, destination, and then the start move time. So now, as mentioned, the Java point has a clone method. The clone returns an object, so we need to cast it. So, and what we're doing is we're just making sure that we have copies of these things. So our our point2D state variables are just going to begin. We're going to initialize them as being sort of not a point, and But in the reset method, we're going to set them to what we actually want. Here we have our initial location and our max speed, which are passed in. And then our reset method has a we're going to set the location, and then this is sort of a nice method that Point2D has. We can give it set location and give it another point, and it will set the coordinates of this point to what the coordinates of this point are without if I literally just set it equal, then weird things can happen. So in other words, I want to preserve the initial location as being fixed, as being a parameter. Likewise, velocity, we can set our location as the two coordinates, and then set the location of our destination to be not a point, and the move time to be 0. So okay, so now our run method. Let's see if I can flip back and forth between. Right, share the whole screen. Okay, so why was I doing this? Okay. So here our move to, we give it our new destination. And so we set our destination to that new destination. Again, being somewhat careful to set the location rather than just setting them equal. And then this is just turns out that if you tell one of these to go to where it already is, then the thing is that it's already there. So anyway, so we're gonna start the move with 0 delay, and then the start move, we're gonna get the start move time is going to be the current sim time. The distance is going to be the distance, and fortunately Point2D we don't have to do the calculations. The Point2D does it for us, which is just the Euclidean distance between these 2 points. And this is why we sort of checked that the distance was bigger than 0, because if the distance is 0, we're dividing by 0 here. So let's see, why did I call that A? Oh, that's just anyway, so the trickiest thing is the velocity calculation here, where we have to multiply by speed, divide by the magnitude, and so that's what this calculation is all about. And then the time is now going to be 1 over that. So what this is the speed over the distance. The delay is going to be the distance over the speed. And then at the end move, we just kind of do that. So in doing the simplest path mover manager, again, it's just straight from the event graph. So here we have our parameter, which is first a Boolean that says whether we start and run, and then an array of these points, which is our path. Our single state variable is actually the next index. So on this, it's fairly straightforward. So we set our path. We reset by setting our next index to be, oops, that should be -1. And then if we're starting on run, we schedule, oh, I see what I did. Okay, and this here the event graph is a little bit different than this is a little bit different than the event graph. What I did was I got lazy and I went here. I went right to the move to. So 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 we're scheduling the move to and then sending the path of the next index, and then at our end move, we increment our index, and if we're still less than our path length, then we go to the next. So why is this path length -1? Because we've already incremented index. That's why. Okay, so let's see how that actually works. So I'm gonna have my initial location at 3040, speed of 25. And so I instantiate a simple mover with those two parameters, and I print it out to make sure that they've gotten in. Here I'm gonna set a path. I just kind of chose like coordinate like 50 -45 -20, but et cetera, et cetera. So send that to our simplest path mover manager with true, meaning we're going to start right away, and make sure that we kind of print it out. And then here, here's where we do this. So notice that the simplest mover listens to the simplest path mover manager, and the simplest path mover manager listens to, let's see, no, the simplest path mover listens to the simplest mover listens to, they're basically listening to each other. And that's how we do this. So here, mover listens to the path mover manager, et cetera. And then we'll listen with a simple property dumper just to make sure that's going on. We're going to run in verbose mode, reset and start. And then that's what we're looking for is, did it in fact go to the right places? So let's check. Oops. That here. Come on. Okay, so our simplest mover just had a okay, so what that suggests is I forgot to huh, that is weird. I know what, yes. On this, I overrode the toString method just to because getting the current location is really kind of what we're interested in here, not so much the parameters. Actually, what I should do is, where are we here? The simplest. Should actually do that instead, because we just want to make sure the maximum speed and the initial location are set to the right place. All right, so let's and And this is just everything that we've been doing. So we have two SimEntity objects. They both have a run method. So that run method is what gets the run event is what goes put on the event list. So we see our last stop location is our initial location, check. Our velocity 0, our destination is not a point, and our start move time is 0. Okay, so now we have the run event from the simplest path mover manager. And in this case, that's scheduled the move to event. Its run event scheduled the move to. And let's see, our first point is 50 minus 45, and it sent the right one there. And now the move to has our destination being that. And so we schedule start move. And now our start move time is still 0 because we have, and then our velocity, it's this kind of weird thing, but it just, the velocity in general is going to be some weird numbers. And then it schedules the end move at that certain delayed time. And then, okay, so what are we're checking to make sure that the events are going to get heard correctly. So at the end move, now we have our start move time being the current time, our last stop location being was our initial location. It's now this 50 minus 45 that we have, and our velocity is back down to 0. So that was the end move event, but then notice that now Simple Path Mover Manager has another point, so it schedules the move to, and sets the the destination to, which is hopefully the next point. And then we just basically have start move, end move, and then for the final one, the final end move event, notice it doesn't schedule anything. It was heard by the simplest path mover manager, but because it reached the end of the path, it was done. Now, for those who are using the Python version, that's pretty much there too. I'll go over it quickly. There's a mover Python file. Now, the thing with because Python doesn't have a point like Java does, we had to kind of write one. So here's the class point, and it just sort of X and Y coordinates. So here I can compute the distance, set coordinates, just some convenient methods like adding two points together, adding and subtracting, the square of the norm and the norm themselves turn out to be very useful. And then the inner product, which is something we will eventually use, and then a scalar multiplication. And then our toString, which Python calls REPR for some reason, is just the value of things. So here's our simplest mover. It has our initial location and then the speed as before, last stop location, velocity, destination. Those are all the state variables. And so reset is going to, as before, set the last stop location to the initial location. And here, actually what this should do is set the coordinates. Do that instead. Here's where, again, it's very helpful to have the method overloading in Java allowed us to have set location where we either give it the coordinates or give it another point where it will do that. Python doesn't allow overloading. As you can tell, my opinion is that it should, but okay. So the run, again, just firing property changes. And then yeah. And then we have the move to the destination. Okay, so yeah, so here I'm the destination argument is without the self, and then the self is just giving a copy of the thing. Probably set coordinates would have been anyway, notify the state change, and then here is schedule start move. And then start move here. We're doing the velocity calculation. And then here's the move time. Here I in the Python version, for some reason, I did all that a little bit more directly. And then we schedule the key thing is this move time. We schedule the end of the move at that move time. Then when end move occurs, it does the whole other thing. And then for the simplest path mover manager, again, a similar type of thing where we give it a Boolean that's going to start on run and a path. And then when we reset, here we have to call the super reset. Here, the Python version is a little closer to how the event graph actually is. So we start at the next index, and then we're going to schedule our next waypoint, etc. So probably I should fix up the Java version of that. But to set all that up, we have our initial location, our speed. So creating our mover, basically the same path, 50 minus 45 minus 20, 100, and 0 minus 35. And then here we in Python it's state change. No, it has sim event listener. We add each one to each, and we'll do we'll kind of we'll run it in verbose mode, and when we run that, it didn't like what I did here. Okay, so let's undo that. Okay, so just verifying that our parameters got in there okay. And then our okay, so the run, and then the run for the simplest path mover schedules the next waypoint in simplest path mover. When that occurs, it schedules a move to, and then here's where we're that move to then is heard by our mover, which is going to schedule its start move event. And that in turn is going to schedule the end move event at the right time, hopefully. And then when that end move event occurs, it's heard by the path mover manager, which then schedules the next waypoint. So here, the next waypoint we'll schedule the move to at our new destination. And we just kind of keep going and going and going. And then at the end, we wind up at our last point. Okay, so verified that in both platforms, at least the basic idea is working. So now, the patrol mover manager is just like the path mover manager, where we give it a path, which is just going to be a list of these waypoints. And the only difference between it and the path mover manager is that when we get to the end, we don't stop, but we actually go back to the beginning. And so, yeah, no, this is not a listener diagram. Notice this is a subclass diagram. So, and then remember that a bold border means that we're completely overriding what the superclass events are doing. So our end move event is always going to schedule the next waypoint until and what it's going to do is we can modulo our index to the path length. So when so in other words, when it hits the path length, it will go back down to 0, and then we'll schedule the path there. So let's look at what that looks like. That is the okay, so we're simply extending the simplest path mover manager. Okay, we have a 0, we have to write the constructors. I mean, that's just one of the things about that. And now basically all we need to do is we're overriding our end move event in this. And so here's where we have our next index is the next index plus 1 times modulo the length of the path. And then we schedule our move to there. And so testing that out, what we're looking for is it to kind of keep going around. Now, you may have noticed that when we're testing the path one, we didn't have to specify a stopping criterion because when it reached the end, it stopped. Here, if we don't stop it somehow, it's going to keep going and going. So I do want to go for at least 10 end moves because that will show me that it's gone to all 3 waypoints, but keeps going afterwards. Oops. Run. Okay, so we have, okay, the run, and then this is all exactly as it was before, but what we're looking for is when it gets to this 0 minus 35 point, that it goes back. Okay, so here's the end move. Oh, okay, so our last stop location is in fact the 035. Here's the end move, and then we schedule another move to at the first point. Okay, and then we keep going round and round and round on this. So okay, so that is verified that piece is working. Okay. And just as before, we have either they listen to each other. And then the final one is I call a random mover manager. And here, instead of having a fixed path, we have a randomly generated one. So so here instead of a path, we have our we have an array of random variates. So this would be an array of ideally, well, just be length 2 because we're in 2 dimensions. And each of those random variates is going to generate the coordinates of the next waypoint. So the idea is that at each end move event, we're going to generate the random coordinates for the next one. So this is basically what it looks like, and I suspect that the Java one kind of was a little bit different, but okay. So so we start off with the destination like that, and so our next waypoint is we're gonna generate this is kind of shorthand for generate from the 0th element of the random variate array, and then this from the first element, and then that's going to create our destination, and then we schedule the move to, and then everything else works exactly as it was before for that. So let's see how that works. Let's see. Okay, so so for this we have an array of random variates, and then our starting on run if we have that. So we set these, and let me check to make sure that I've okay, notice that I have cloned them, so you want to clone them. Okay, so here's how we have our, if we're starting on run here, I go right to the new destination, and it's a 0.2D double where we generate the first coordinate and then the second one, and then we schedule a move to for that. So and then at the end move, we simply generate another random point and then move there. So that's really all there is to it. So for the random one, just as before, we need to, how are you doing this? Okay, let's stop after 5 end move events. Okay, so if the coordinates are these going to be these sort of very weird ones. But okay, we have a start move, and then a move to, then a start move, and then an end move, and a start move, etc. So they were just flipping back and forth between those. And notice at the time, kind of unlike a time step that kind of goes in certain increments, the times are whatever they are. And similarly for the Python version, okay, that was the path mover manager. And then the random, the random mover manager, we give it a coordinate generator. And then our destination is just going to be a new point with the coordinates there. And then our end move event is going to be simply scheduling the next move to. And because it is, yeah, that's really all we need. So the tests on these. So here, just to be obstinate, our x coordinates are going to be uniform between 0 and 100, and the y coordinates are going to be normal with a mean of 0 and a standard deviation of 10. And so if we run that, we see that, simply, again, just kind of generate some things in here because I had control over the toString for the point. I can kind of have them be a little less nasty. But we're just kind of generating these points and just going from start move to end move. And the times are hopefully more or less correct. I think again we stopped after 10 end move events. So okay. So now just to kind of in other words, in order to kind of check and make sure this is all kind of doing it properly, it's important to kind of have to be able to kind of work it out by hand. So let's say if you had a mover located at say 20 minus 30, and at time 0 it starts moving to minus 1060 at a speed of 30. And so some questions that these are things that we'd want to verify if we were kind of running it. What's the velocity of the mover during the move? When does the mover arrive at its destination? And what is and here's the other thing is that what is the mover's location at time 20? I'm sorry, at time 2. I think I might have forgotten to do this in the Python version, so I'll have to fix that. So here, remember we talked about implicit state, which is in this case current location. So from the outside, this looks like it's a state variable, but inside, of course, it isn't. And here we compute the if I want to find where the mover is at any point in time, I based upon the state variables that it carries, I can compute that. So the elapsed time is the current time minus when we started. And the point is the place we're at is our last stop location plus the elapsed time times the x coordinate of the velocity vector. And then the y coordinate would be the same times the coordinate of the y coordinate of the velocity vector. So, okay, so let's, just based upon our data, our velocity, to compute our velocity, first we take the difference in distance. And so that would be minus 3080. And then we take the magnitude of it, which is the Euclidean distance of this, which is the square root of the squares. And so here, 10 root 73. Just for numerical examples, it's always best to kind of carry around the highest precision. In other words, don't round off until the very end, because especially with calculations like this, if you round off too early, then the results can be off by a bit. Okay, so having done these two, we divide our distance vector by the distance and multiply it by the speed. And so we wind up with this. So this is here's our difference vector. Here's our magnitude. So this is a unit vector in the right direction. Multiply it by the speed of 30 in this case, and we get this value, and then at the very last minute is when you should unravel the thing. Okay, so there's our velocity. And using this information, we can also do the travel time. So the distance was 10 root 73. The speed was 30. So we have root 73 over 3, which is approximately this. So now, and this is kind of the, in a way, the punchline of this whole thing is that the location at any given time, we can compute exactly, and by exactly, I mean up to computer precision, by using the equation of motion, which for a simple linear system is just the starting point plus the velocity times the difference. So we started here. So our location at time 2 is the difference, or I'm sorry, our starting point plus our velocity times the elapsed time. So we started at 0, so the elapsed time is still 2. And then when we unravel that, we have the 20 here minus 180 over 73. And then the second would be minus 30 plus, multiply the 2 plus 480 over 73. So it's approximately this. So that's how we do a numerical example. And that is it for today. So again, no lab this afternoon. My apologies for for being somewhat less cogent than normal, or although maybe you didn't notice, maybe this is bus is always this this confused. So yeah, I've been under the weather for this. So so I don't have any torture for you for the weekend. But I think there's still an outstanding written assignment, which is due tomorrow. Anyway, so if there are no questions, I will adjourn.
I did have a question, sir.
Yes.
Is there any chance that we can get that due time extended to close of business tomorrow, vice 9:25?
Oh, was it 9:25?
9:25
Sorry.
a.m. Yes, sir.
Oh, that was my mistake. Yeah, no, it should be close of business. My apologies. I'll fix that.
Thank you, sir.
Yeah, close of business. Yeah, I mean that's been the standard. Thanks for pointing that out.
No worries.
Okay. Anything else? Okay. Bye-bye.